morning, everyone. So the last presentation of this atelier will be about a project that we did for the Office of Mobility in the canton of Basel-City. I'm working for the statistical office there. And what we did is make a prediction tool that is easily usable for site developers when they plan parking spaces in new area developments. And this is an example of how we can easily make insights from data available within the canton, and it's easy to use these insights with rather limited resources. Why is this relevant for site developers to plan parking spaces more accurately? In urban areas, space is limited, and we have mobility and parking space strategies that try to use public spaces more effectively for various uses. And we have cars take up a lot of space, and so they approached us because they want to know, is there a way to predict variation in car ownership so that they can better plan parking space in larger area developments, such as the ones you see here. On average, the car ownership in Basel City is 0.5, and this is also the rule of thumb that they use to plan parking spaces. By law, there can be one parking space built for each household, but yeah, different households have different car ownership rates, and so we try to help them to improve their planning. We used data that we had available. The data set that I used was already prepared by my colleagues Matthias Minke and Jose Monteiro for another project where they looked at littering in public spaces. And so we take various linked administrative data and model the rate of car ownership in the city of Basel. The model has a rather fine spatial resolution at the level of buildings, and it considers location as well as resident-specific characteristics. And then we take these model results and we transform them into a prediction tool, at the moment easily implemented in Excel. It could be more fancy with more time and resources. But this is a very straightforward way to provide the results to the site developers. And at the time of planning, these site developers usually have rather limited to no knowledge about the future residents. So this is really a balancing act of how can we make insights about households and buildings available to them when they actually don't know much. So they will have to make assumptions, and we have to take into account what information they have available. As I said, on average, there's 0.5 cars per household, and so we're going to try to make something out of variation in car ownership in the data. Let's have a look at this. So this is a map of Basel City. You see car ownership rates per household. In various areas, there's obviously some variation. There's places such as the inner city where there's fewer cars per household, and some regions with more cars. Then there's also some outliers within districts. So this is something we can take into account. Another factor that site developers usually have available is how large the building is going to be, so how many households there are going to be in a building. Here you see the number of households per building mapped against the number of cars in a building. Obviously, there is a positive correlation. And here you also see that we have rather few observations of larger buildings, and these are going to be the relevant observations for site developers because the new area developments are rather larger buildings than the ones we have so far in the city. So we're going to have to be making out-of-sample predictions. Another information that site developers have available is the floor area. So the total floor area of the building. Here you see mapped the total floor area dedicated to residential use, mapped against cars per household per building. So you see in smaller buildings, there's much more variation. Those are also single-family houses that tend to have more cars. And then the larger the buildings get, we have fewer observations, and the car ownership rates kind of settles at around 0.5. Looking at variation across income categories, we see that obviously, or as we would assume, not obviously, but it is what it is, there's a positive correlation between income and car ownership, and we see particularly in high income categories that there's much more variation. So there's something we can work with. The data set consists of various data sources, so we link household characteristics coming from population registers, such as the number of households and the residents per buildings, as well as household types, age structure, and share of foreigners. And we also add data about the total net income in the building from tax statistics. This is a factor to take into account, so we calculate average income per person based on the total income in the building and the total number of people in the building. We link this with building characteristics from the buildings and dwellings register, so the building category, the floor area, and the total size of the living space of a building, together with spatial characteristics such as the distance between a building to the closest supermarket, as well as the quality of access to public transport. We take this to a model. This is the setup. So the observational unit is a residential building in the city of Basel, and the data is for the year 2023. And we have household characteristics. This is information that is not so much available to site developers, so they will have to be making assumptions about this. And then there are the building and spatial characteristics, which are more readily available to them. And we assume a Poisson distribution, and this is the model then that we estimate. Most importantly, what are the requirements that we have for this model? First of all, we want to reduce the model prediction error. And as these new area developments tend to be larger, we are going to be making out-of-sample predictions. So on one hand, we want to have a really good model fit, but we have to be a bit pragmatic and balance it with practicality. Because what we're going to do in the prediction tool is that we're going to hold some of the explanatory factors constant, and then the site developers are able to specify some of the values of the variables that they are interested in. So for the variables that site developers are going to be specifying in the tool, we want to have high accuracy of the estimation of these coefficients, and the variables must be easily specifiable as well. So when kind of choosing in which way the variable is going to enter the model, we had to find a practical way as well. In the end, the model that comes out looks like this, or the model fit. On the x-axis is the observation, on the y-axis the prediction, and on average it works pretty well, but obviously we're more interested in the variability, which I'm going to go into detail a bit later. The biggest challenges of this were we had to really customize this to the site developers. And as I mentioned, they had limited information, so we kind of, especially taking into account floor area, for example, there's not really, if you think about it, not a particular reason why it would be related to car ownership, but it could capture some other relations if we take it into the model. Then for the variables that are not specified in the prediction tool, it was also important that we choose reasonable values for these when we make predictions, and they have to become consistent in combination with the variables that are specified in the tool. So for example, when the share of household types are specified in the tool, if the site developers decide that they want to look at a building with only family households, we have a control variable for the share of people below the age of 20 in the model. So if we will keep that at the average, it might not be representative. So if site developers specify the share of family households in the prediction tool, then also the share of the age distribution has to be conditioned on the specified variables. The limits of this model are, of course, there's always a model error, and the out-of-sample predictions, they are, of course, driven by the model assumptions. And we also have to take into account that the model obviously is based on observational data. Behavior is changing. We cannot account for that, as well as not for any changes in urban policy. But this is a good way to take what is out there at the moment and support these site developers. What it looked like in the end is, so we took the model coefficients and we prepared them in this very simple to use prediction tool. So the site developers can specify some of the variables, such as the number of households. That is a really important variable for them. So this kind of shows you the size of the building. They can specify the building category, the district. They can choose averages. And as you can see here on average, we're exactly at 0.5 cars. Not that interesting. It gets interesting when they start looking at the variation. And you can see that we find significant correlations between some of the household characteristics and car ownership. So we really want these site developers to play around with the model and get a better sense. To conclude, we built this prediction tool for site developers, and it is especially useful when used for predictions that are not for average households, so that space can be used more economically. And it is also really important that the prediction tool is used in combination with all the priors that site developers have, because they have a lot of other knowledge. And then also just take into account, we're looking at cars and parking spaces here. That's a bit of an egg and chicken or egg situation. So are the parking spaces, or are we predicting parking spaces because the cars are there, or are the cars there because the parking spaces are there? So there's going to be sorting effects. People tend to move to houses that have parking spaces if it's important to them. If there's plenty of parking space, it can be an incentive to buy cars. But it's also really useful for these urban planners, because they want to move cars from public grounds to private grounds. And so by making better predictions of parking spaces, they might be able to improve the situation. Thank you.